Hello there, and welcome to our next lecture in our series of lectures. We're off to chapter 2 today. Chapter 2 is all about the measurements. Perhaps we'll measure how big this stool is. Maybe we'll measure how long the floor is. But you'll learn how to take accurate measurements in this chapter, along with some other important things like significant figures, conversions, and our good friend density. This recording is going to be broken up into two lectures. One is this one right here, the first recording. Then, way over there, maybe not so far, we will have our next recording after this one. So make sure that you watch both lectures for chapter 2. Other than that, I'm not going to be here too long, other than say, have a good lecture. Off to you, Professor. All right, welcome here. We're going to do chapter 2 here, which is about measurements. So in this chapter, we're going to talk a lot about, obviously, measurements, how to take proper measurements, everybody's favorite thing, significant figures. We'll talk about scientific notation. We will also get into temperature conversions, conversions in general, dimensional analysis, and we will wrap up the chapter here, I think, with some talk of density. This chapter does contain a lot of information. So unlike chapter 1, I think this recording will probably be broken up into maybe a couple recordings or so. A reminder that I'm going to try to kind of keep these to like you were in person, maybe an hour and a half or so sort of lectures at a time. I think that's really manageable and things that you can watch and be convenient to sort of watch and follow along. Speaking of following along, a reminder again, as we mentioned in sort of the first lecture video and probably many times before that as well, it's really important that you do go to Canvas, you download the lecture notes here, and that you do follow along and you do pause the video when we do get to examples. You try it yourself. The best thing you can do, again, is work things out on paper with a pen or a pencil and a calculator. So when it comes to exam time, you know how to properly, again, punch these things into your calculator, do these problems. You probably will not get the most out of these lectures if you just simply watch them and don't actively participate. So although it is online here and the lectures are online, there is still a participation component to it that's really important, not only for the class, but really for your success in the class. So once again, I would highly recommend that you download those on paper and work them out, or at minimum, at least download to your tablet. And what your style is, make sure you pause the video and work it out as well. So it's really the best way to learn in chemistry is to actually do it rather than watching somebody else do it. All right, so with that saying said, let's see how far we get, at least here on the first part of chapter 2. And we're going to talk about measurements. So let's get into it. So whenever we take a measurement, it's really important not only the actual value that you get, the number that you get, but units. Units are pretty much almost, if not more important than the numerical value that you get. It is extremely important because it really gives the person that is looking at that number that you recorded a frame of reference of what it means. So a very simple example would be, for example, if I just said, hey, I have 100. That's lovely, but what does 100 mean here? 100 could be, I have $100, which would be good, I think. It could also mean I have 100 apples, which might still be good if we like apples, maybe making some apple pies or something like that. Could also mean I have 100 pennies. I could have 100 pieces of gum. Whatever it may be, I really have no frame of reference for what that 100 means, other than 100. So it is incredibly important to, whenever you take a measurement or record a measurement, there should always be a number and there should always be a unit associated with it. The unit, again, gives the person a understanding of what we're talking about. Now, when we talk about units, there actually are two widely used sort of versions of units. There's sort of the English system is sometimes referred to, and that is used by the United States. And then, pretty much everybody else is rolling there with the metric system. The metric system is pretty much used by almost everybody else outside of the US. So obviously, as you can imagine, if, as the world got sort of smaller, people are sort of doing business and dealings across sort of countries, it would be very bad that we have sort of one person using English system of units, one person using the metric system of units. So that could really lead to problems. So in 1960, they actually had a conference on weights and measures. That sounds like a lot of fun, I suppose. And they actually came up with a sort of standardized system of units that's oftentimes used in sciences like chemistry. And that is what is sometimes referred to as the International System of Units. It is sometimes abbreviated as the SI system of units, which is basically the Le Système International. There we go. I gave it a try. A system of units. And for all intents purposes, it's pretty much based off the metric system. So it's pretty much based off the metric system. So a lot of times in chemistry and science, you'll sometimes see the SI unit is this, or, the SI unit for mass is this. And that's what they're referring to is, it's basically kind of based off the metric system. So again, even more important, if you had 100 kilograms versus 100 pounds, that is very different in terms of what it represents in terms of mass. So units are really important. The type of unit that you use also really important as well. So units are really critical parts of measurements, but also really critical is understanding what the units represent. So, for example, there's some SI units that are sort of standard units that we use for different types of measurements. So here for the length, it is the meter, which is abbreviated with an M. For mass, mass is kilograms, is the SI unit. Temperature is a unit that you might not be familiar with. It is actually the Kelvin, which is abbreviated with a capital K. Time you probably are familiar with, which is seconds. The amount of a substance is something we'll talk about a lot in some later chapters. That is the mole. Electrical current is the amperage. And we don't really use it all that much, but luminance intensity is candela, which I would say we probably won't see too much in here. It's funny that it sort of found its way up on the chart here, but we probably won't see it too much at all in chemistry or probably any of the chemistry classes that you take for the most part. But definitely length, mass, temperature, time, amounts of substance, and electrical current are things that very commonly units in chemistry that we use a lot. It's really important to know what a unit represents. So, for example, I can't tell you how many students have come up to me and said, yeah, I had, 150 kilograms of volume, and kilograms is not a volume, it's a mass, or vice versa. I had 150 milliliters of mass. And again, milliliters is not mass, it's a volume. So it's really important to have sort of the recognition of what a unit is and what it represents in terms of the quantity that it represents. Is it a mass? Is it length? Is it temperature? Is it time? So make sure that you do get into a habit of understanding what the unit represents and, what you're talking about. So, there's no misunderstandings. So let's talk a little bit about some of these quantities of measurements that we make. The base unit there for length is a meter. 1 meter is about 39.37 inches. Some very common conversions or qualities that we use with length are length units of centimeters, decimeters, and kilometers. I would say a lot of times in chemistry, in terms of length, we definitely come across meters a lot, centimeters, and kilometers. These are ones that we do run into a lot in problems. Some relationships, 1 centimeter is equal to 0.01 meters. That, by the way, is the same thing as saying 100 centimeters is equal to 1 meter. And if you're not sure how you get that, you divide 0.01 to both sides, and you will have your 100 centimeters is 1 meter. So I would definitely say whichever version of that that you want to remember or go to is something that you'll use a lot. Most people will kind of use the larger number. The 100 centimeters is 1 meter, and that is, again, something that we use a lot. I would also say over here, this is something that we use a lot, which is 1 kilometer is equal to 1,000 meters. So that is, again, another conversion that is used a lot. This is that 0.01 written in scientific notation. We'll talk a little bit about scientific notation coming up, but that's just another way of expressing 0.01. Same thing here, scientific notation. Scientific notation, another way of expressing these numbers here that we see. So definitely, those are two sort of really good length measurements and kind of conversions or equalities is really what they're referred to that we do come across a lot. So that's a good thing to kind of keep in your head as you kind of go through these chapters and chemistry in general. Now, because really the SI system and the metric system, we sometimes will use prefixes to help us sort of get rid of some of the zeros along the way if we had to kind of go from one prefix to the next. So there's two sort of equivalents that are used. A lot of times people will use the exponent sort of equivalent. And this is really kind of in scientific notation. And a lot of times you'll see a table like kilo, for example, is 10 to the 3. And deci is 10 to the minus 1. So it's really important when you kind of see something like that, for example, and we'll see it a little bit later on as well in another table, I think, when we see something like kilo, you'll oftentimes see it in a table. That is 10 to the 3. And sometimes people always want to kind of use this backwards. And what I mean by that is when you see something like that, like we see here in this table, what that 10 to the 3 is, and by the way, that is 1 times 10 to the 3 on your calculator when you need to put that in to do a problem. What that really means is in one of the prefix units, so for example, kilometers would be the prefix unit. That is how much there is of the base unit. So there would be 10 to the 3 meters, and meters here is the base unit. And by the way, this sort of conversion works the same regardless of what the base unit is. For example, if I had 1 kiloliter, that would equal 10 to the 3 liters. Again, in one of the prefix units, that is how much there is in one of the base unit. It is a very common error that people make, which is they always want to do it backwards. Like, oh, there's 10 to the 3 kilometers in 1 meter, and that is incorrect. Don't do that, or you get the big X, and you don't want that. So make sure that whenever you kind of see this exponent type of conversion used for prefixes, like kilo, milli, centi, whatever it may be, that is how much there is in one of the prefix units to one of the base unit. So for example, here, when we roll to milliliter, the prefix here is milli, and basically milli represents 10 to the minus 3. So once again, in 1 millimeter, there would be 10 to the minus 3 meters. And again, prefix unit, base unit. And that's the proper way of doing that. So those are some common sort of conversions. I would say, again, in chemistry, kilometers, something we use a lot, meters, centimeters, millimeters, and nanometers is used a lot. So those are used a lot in terms of length. And we'll talk more about, I think, conversions coming up here and how to use that. But I did want to kind of point that out since we kind of have this slide here. But it's really important not to get those things backwards. It's a very, very common sort of error that people make.
Here is sort of the difference between the English and the metric system. That's a ruler, by the way, in case you missed it. But a ruler here, a traditional ruler, on the big part there are inches. So there's our 1 inch. And that is a exact conversion. So 1 inch, which is the English system, is equal to 2.54 centimeters exactly. And that's what we see if we come straight down. 2.54 centimeters, which is what the big numbers on the bottom are. Those are centimeters. So I guess the bonus question here, or the double jeopardy question, is what on earth are the smaller markings represent here on a ruler? Well, we already know the top part here are inches. The big numbers there are centimeters. The small little dashes are our friends millimeters. So as you can count, there's actually 10 millimeters in 1 meter. So if we look here, for example, between 5 and 6, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 millimeters and 1 centimeter, right? And so the little guys represent basically the millimeters, which means if we come out to here, you're looking at this 2 being 20 and the 5 being 25. So you're looking at something like 25.4 millimeters would be the conversion there between those two. So it's always good to know how to properly look at a ruler. And again, on the centimeter scale, you also have millimeters, which are the smaller numbers that are there. So let's talk a little about volume. Volume is the amount of three-dimensional space that's occupied by a substance. Volume is length cubed, and the SI unit is meters cubed. So you may be wondering, what does that mean? Sort of volume is length cubed. So there's several different ways, as we'll talk about, especially in this chapter, that you can kind of get a volume. Very common unit of volume is milliliters. And milliliters is a very common unit of volume for liquids. And frankly, a lot of times we just get the volume by taking an actual reading of where the volume is in some type of piece of glassware. Now, if we have a solid, we usually don't get the volume that way. A lot of times we can actually get the volume of something like a solid by actually taking 3 different length measurements. We could take the length of the object times the width of the object times the height of the object, especially if it's like a cube. And if we measure each of these in very common units of, say, centimeters, and this guy is measured in centimeters, and this guy is measured in centimeters. When we take centimeters times centimeters, that is equal to a cubic centimeter. This measurement here, which is a cubic centimeter, is an actual volume. Each of these individual measurements here of length and width and height, each of these individual measurements are measurements of length. So if you take 3 length measurements and you actually multiply them together, that will give you the volume. And that's a very common way that you can really get the volume of some type of cube. If you have a little wooden square cube and you wanted to get the volume of it, you could take those 3 length measurements, multiply them together, and you will get a volume. Now, there is an important relationship between those two things, which is what we see here. 1 milliliter is the same as 1 cubic centimeter. So it is a 1-to-1 relationship, and that relationship we do use a lot. Some other important volume units that we use is liters. And this relationship here is one I can't tell you how many times we use it, but a lot. 1 liter is equal to 1,000 milliliters. So that is, again, another very important unit conversion that we use a lot. So those two in the boxes are something that you'll see a lot in chemistry. 1 milliliter is the same thing as a cubic centimeter. We'll also see it a little bit later as well, but we'll talk about it here too. It's also sometimes referred to as 1 cc. That also sometimes refers to as a cubic centimeter. 1 liter is 1,000 milliliters, is pretty much in most calculations that you do that involves volume. Those are probably one of the 2 units that you have to put the sort of volume in, is either liters or milliliters. So those are very, very super common sort of units. Let's talk a little bit about mass. Mass is the quantity of matter that is present in an object. Matter, as we talked about in the previous chapters, basically anything that occupies space and has mass. The fundamental unit of mass is actually the kilogram. And also a reminder that we do use some different units here, and these are the same prefixes, so very similar to what we were just talking about with our length. We have kilogram, and once again, the prefix here is kilo, which is 10 to the 3. So once again, in 1 kilogram, there is 10 to the 3 grams. That is also the same thing as saying 1,000 grams. That's basically what 10 to the 3 represents, is 1,000. That's a very common one. Milligrams as well. Once again, that milli is the same milli conversion we saw previously. 1 milligram is equal to 10 to the minus 3 grams. This is also the same as 1,000 milligrams is equal to 1 gram. And once again, we get that by dividing 1 times 10 to the minus 3 to both sides, and you get your 1,000. You might recognize this again. That is the same as the conversions we just used for volume. So again, 1,000 milliliters is the same as 1 liter. So, again, the base unit, which happens to be liters here, which is a volume, versus here, which is a mass. The base unit is grams, but the conversion, or the way to go from sort of that prefix to that base unit, is the same. So again, in terms of mass, kilograms, centigrams, grams, and milligrams are really most common. Probably those 3 kilograms, grams, and milligrams, probably the big 3 in terms of mass units that we very commonly come across. Now, there is a difference between 2 words that are sometimes used a lot and sort of interchangeably used, and a lot of times not correctly. There is a difference between mass and weight. So weight refers to the force that gravity exerts on an object. Mass is sort of independent of the force of gravity. So when we do weigh something, which sometimes confuses people as to why they sometimes will use weight, we're actually getting what we like to refer to in chemistry as the mass of the object. Now, what is the difference between the two? Well, the mass of the object would be the same regardless of where you're at, but the weight of something would be different. So as the example there says, for example, if you weighed an apple here on Earth versus what it would weigh on the moon, the force of gravity is different in both locations, so the weight would be different. But technically speaking, if you took out the force of gravity, the mass of that object would be the same. So the take-home message here is, in chemistry, that is the terminology that you should use when you do weigh something on a scale or a balance. We do refer to it as mass rather than weight. We kind of take out the idea of the force of gravity exerting on it. So let's talk about some important conversions, and the 3 sort of important conversions, first off, has to do with temperature. And there are three major sort of temperature scales that we commonly come across here in chemistry. The first ones is degrees Fahrenheit, which is abbreviated degrees F. Degrees Celsius, which is degrees C. And lastly, the third one, which is what sometimes used to be referred to as the absolute temperature scale, is now referred to as the Kelvin temperature scale, which is K. One major difference that you might see between the three of them, or really one out of the three of them, is when we do sort of use Fahrenheit, we do refer to it as degrees Fahrenheit. When we do Celsius, it is degrees Celsius. When we do Kelvin, no degrees. So we do not put the degrees symbol. We do not say degrees. We just say something like 273 Kelvin is basically what we kind of do. The Fahrenheit scale, water boils at 212 degrees Fahrenheit. It freezes at 32 degrees Fahrenheit. And that's the scale we oftentimes will use when we're taking our temperature, the weather outside. Again, it's widely used in the US and Great Britain. The Celsius scale, which is the metric system, water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. In chemistry, we use Celsius a lot, or degrees Celsius a lot. And these two numbers here are kind of important numbers that you should kind of keep in the back of your head as you try to travel through chemistry and take different chemistry classes. The boiling point basically of water is 100 degrees Celsius. This is liquid water, obviously. And the freezing point there of water is 0 degrees Celsius. So those are two very common numbers that come up in a lot of different applications as you go through chemistry. The third temperature scale out of the three, pretty much outside of this chapter, is pretty much going to be this guy. It is Kelvin. Off the top of my head, pretty much 99.5%, even higher maybe, of any type of chemistry formula that you need to use, chemistry type calculation that you need to do. If it involves temperature, it usually needs to find its way into Kelvin. So that's also something you should keep in mind as you go through chemistry classes. If it's temperature, probably that Kelvin is where you need to get it into to put it into the formula you're trying to use. And that's oftentimes, as we'll see in some of these other chapters, when we start doing calculations, even in cases where they give you a number in Celsius, they ask you to give the answer in Celsius. A lot of times you need to get it into Kelvin, put it into the formula, and then convert it from Kelvin back to Celsius. So sometimes people get tricked on that. Water boils, by the way, on the Kelvin scale, which used to be the absolute temperature scale, there at 373 Kelvin and 273 Kelvin. Let's take a look at the differences here between the boiling point and the freezing point, and really the differences between where water boils and freezes on these different scales is really the difference between how we convert between the different scales. So looking at Celsius and Kelvin, you got about 100 unit difference between the boiling point and the freezing point. Looking at Fahrenheit, it's 180 degree difference between the boiling point and the freezing point. So that's really what makes the difference in how we convert between these things. So let's talk about doing these conversions. So the first conversion here is to go between Kelvin and Celsius, which I would say is, again, probably your main conversion that you're going to do in most cases. To take the temperature in Celsius and you add 273 to it, and that will give you your temperature in Kelvin. The true conversion, by the way, is 273.15. That is really the true number. The correct number, I guess, is the way of saying that. And if you see this number here, okay, so the, again, correct number here is 273.15. So if you see this 273.15, that is really the right number for the conversion. I would say most people, and I am okay with it if you use just 273 as the number. Some people will use the entire thing. A lot of times what will happen is that 0.15 will get kind of rounded off anyways. Some people I've even seen sort of round to this number, 273.2. So you can pick whichever one you want to do. I personally, most of the time, will roll with just 273. But again, if you see that 0.15, that really is the true number that should go here and is used. So this is very important conversion because, as I mentioned before, that temperature in Kelvin really is the most popular sort of one that's used. And again, you take the temperature in Celsius plus that 273. Now, obviously, if you do have a temperature in Kelvin and you need to give the answer in Celsius, which is used a lot in chemistry, our temperature in Celsius would then be our temperature in Kelvin minus 273. And we get that by simply subtracting the 273 to both sides. That cancels that out and that gets us over here. So knowing both of these, really important, as those are really the conversion that you're going to use the most outside of this chapter. Again, probably not going to see too much Fahrenheit and Celsius, but let's talk about the conversion between Fahrenheit and Celsius. If you have the temperature in Fahrenheit or Celsius and you want to convert it to Fahrenheit, it is 1.8 times the temperature in Celsius plus a 32. And that means if you want the temperature there in Celsius and you have Fahrenheit, we're going to subtract the 32 to both sides and then divide by the 1.8. And that's going to give us what we see there. Temperature in Celsius is the temperature in Fahrenheit minus 32 divided by 1.8. So these two are really important as well. By the way, the 1.8 is the same as 9 over 5. So if you take 9 divided by 5 on your calculator, you get 1.8. And that's maybe something that you learned in terms of temperature conversion. So that is also used. So when we do a temperature conversion, it's really important to remember how we should give the answer. And because there's a lot of variability in terms of these conversion formulas that we see here, we oftentimes will follow a general rule in terms of how our answers should look at the end. And this is a situation where all you are doing is simply converting from one temperature unit to the next. And what you should do is usually make the converted temperature look like the original number. So what that means is if your original temperature value was a whole number, when you convert it, it should convert to a whole number. If your original temperature value went to the first decimal place, you should take your converted temperature to the first decimal place. So once again, that is the general rule that we follow. It is not the strict significant figure rules that we're going to talk about in a bit here in this chapter, but that is a general sort of practice that you want to follow in this case. So let's take a look at some examples here. So why don't you take a moment here. Again, this would be a good time to pause the video and give it a go and do these conversions. So why don't you take a moment and see what you come up with, and then we'll take a look at them here together. Okay, so hopefully you took the time to work these out once again on paper, or grab yourself a handy dandy calculator if you didn't have one in front of you, and let us give this a go. So on this first one, we are looking at degrees Celsius, which is what's given to us. We want to end up in Kelvin. So that is our temperature in Kelvin is equal to our temperature in Celsius plus our 273. So our temperature in Kelvin here will equal 28.5. plus our 273. And that's going to get us here 28.5 plus a 273. That's going to look like 301.5 Kelvin. Once again, here, a couple of things. There is no degree on that, so it's just Kelvin. Original number here, 1 decimal place. Converted number also to 1 decimal place. So that is what I was just talking about. You want to make sure that your converted number looks like your original number. Looking at the second one here, we have, again, degrees Celsius given to us. And in this case, we want to get to degrees Fahrenheit. So that would be our temperature in Fahrenheit is equal to 1.8, our temperature in Celsius, plus a 32 here. Putting in our numbers here, 1.8 and our 41 plus a 32. That's going to give us 1.8 times 41 plus a 32. Going to give us 105.8 degrees Fahrenheit. Now, this is a situation where my original number here was actually a whole number, which means here I would actually want to take it to 106 degrees Fahrenheit, making this to a whole number, which would take us here. That's an 8, so we're going to round up in this case and to 106 degrees Fahrenheit. Here we do need the degree symbol for our Fahrenheit value. Lastly, here we got pork at 160 degrees Fahrenheit, and we want to convert it to Celsius. So our temperature in Celsius is going to be our friend Fahrenheit minus 32. We're going to divide it there by 1.8, and that will get us our 160 minus 32 divided by 1.8. Gets us 160 minus 32 divided by 1.8. Going to give us on our calculator 71.1111. I got a lot more ones actually. 111 degrees Celsius. Once again, here we're looking at a whole number. So in the case of temperature conversion, 71 degrees Celsius would be the proper way to do that. So once again, and this again is specific for just temperature conversions. If you're just simply taking one temperature value to another and not really doing anything else with it, the general rule is whatever the original temperature value looked like, your converted value should look very similar to it. All right, so continuing on here, talking about some different types of units. Let's take a moment here and think about what each of these units represent in terms of what type of unit we're dealing with. So here, we're really looking at our K, which is Kelvin. So that is definitely a temperature that we're looking at. Here, the unit is L, which is liters. So that is a volume that we're looking at. M is not mass, I was going to say, but that's going to be meters. I'll try to spit that out. So that's meters, and that means that that is a unit of length. And lastly, speaking of mass, that is going to be kilograms, and that is a unit of mass. So as I mentioned before, it's really important to have an understanding of what these units represent and what type of unit it is dealing with. So let's take a look at some of these SI units that we talked about. Temperature is Kelvin. Length is meters. Mass, the SI unit there is kilogram. So again, that sort of unit and what it represents is really important to understand that. So speaking of observations and measurements, there's two types of sort of values that we come across, and that's qualitative and quantitative. Qualitative consists of just general observations about a system. Maybe it's purple, maybe it has polka dots, maybe there's rainbows, whatever it may be, stars, that type of thing, a solid form, and those type of things. Now, when we do take a measurement, that is more quantitative, and quantitative is comprised of numbers and values that you get through some type of measurement that you take. So a quantitative observation, as you can see there, is a measurement. And when we take measurements or record numbers, sometimes we do need to record numbers in a special way. And that special way is what is sometimes referred to as scientific notation. And scientific notation is a way that we handle a lot of times really large numbers and really small numbers. So, for example, there is 6022000000. I lost how many zeros at this point. Hydrogen atoms and 1 gram of hydrogen. It also has a mass of 0.00 lots of zeros, 166 grams. So when we deal with these kind of really large numbers, which is that, and a really small number, a lot of times, if we were going to try to keep that number the way it is and use it in calculations, there's a fairly good shot that we're going to lose some zeros along the way, and we don't want to do that. So a lot of times we use scientific notation to help us sort of get around that. And scientific notation has a general formula of n times 10 to the n. And this first n is a number between 1 and 10. And that means 1's okay, 10 is not actually. So it doesn't need to be a number between 1 and 10. It cannot be 10, 20, 100, 200. Also, it can't be less than 1 either. So it can't be like 0.9, 0.8 or anything like that. So it's got to be at least 1, but not 10. So somewhere between that. Times 10 to the little number here. And this little n is either a positive or a negative number. And it really depends on your decimal places and how many decimal places you needed to move to basically get yourself to a number between 1 and 10. And again, depending on which way you do that, maybe a positive exponent or a negative exponent. So again, if we have 325, there's no decimal written. We do assume it's right there. And we would need to go one place. That's only going to give us to about 32.5, which is not a number between 1 and 10. We then would have to go one more place. That is going to give us a number between 1 and 10, and that's going to be 3.25 times 10. And we moved it one place, two places to the 2. And this would be the proper scientific notation. In this case, since we moved it to the left, to turn it into scientific notation, we end up with a positive number there for our exponent. Now, if we had something like 0.032, in this case, we would need to go one place, gives us 0.3, so not a number between 1 and 10. We have to go one more place, which gives us 3.2. That would give us 3.2 times 10. And again, we moved 1 and 2 places. But this would be -2 as we move to the right. We end up with a negative number when we put it in scientific notation. Now, one way you can remember that is pretty simply, if it's a large number, pretty much anything above 1, it's going to be a positive exponent. And if it's a small number, anything less than 1 will also be a negative exponent. So that's a way that you can remember that. Also really important, speaking of sort of small numbers, it's also really important to make sure that you do write that kind of extra 0, if you will, before the decimal. So that is really good practice, and not just write numbers like this without that 0 there, because when you're doing a lot of sort of calculations, before you know it, numbers run together and you're not really sure. So it is proper, and you should do it in this class and every chemistry class that you do, Make sure that you do include that 0 before the decimal, just to kind of make sure it's clear where one number starts and another number sort of ends. So as I mentioned, scientific notation has that general form of n times 10 to the n. And again, that positive or negative depending on which way you are moving. It is opposite, by the way, if you're kind of going the opposite way and you're moving from, say, scientific notation back to positional notation, which is what is sometimes referred to when you just write it as a decimal sort of form. So 3, when I look at this, I know it's a positive number, which means it's going to be large. So the only way to make this number larger is I need to kind of go this way and put some zeros in there. And that would give us 1, 2, 5, and 0. And that is a larger number. Obviously here, if I had the opposite, -2 means that it's going to be a small number. So once again, I actually need to go the opposite way to make that smaller. And that would give me 0.0125. Once again, -2 going the opposite direction. So it's important to remember which way you need to go. And again, just simply thinking about it as positive means large number. So you know if you're going the opposite way, you got to make it a larger number by putting the zeros at the end. And if it's a negative number and you're kind of going the other way to put it into positional notation, you got to kind of put the zeros at the front to make it a smaller number. So you do need to be able to kind of go both ways. The question might be as well, do I need to write all my answers in scientific notation? And the answer to that question is actually, for me, no, you don't actually have to do that. Some teachers do want you to do that, kind of give all your answers in scientific notation. But for me, you do not need to do that. Obviously, unless the problem says give the answer in scientific notation, then clearly you should give it in scientific notation. I'm more importantly looking at, are you going to give the answer to the correct number of significant figures, which we'll be talking about shortly. With that being said, you should also note that there is sometimes only one way that you could give an answer to the proper number of significant figures, and that is to use scientific notation. Because with scientific notation, when you do actually write a number in scientific notation, all of the numbers before the times 10 part, for example, just put a 4 there. All the numbers before the times 10 part, which in this example here would be these 3 here, are significant figures. That would mean in this particular case, this guy has 3 significant figures. So what does it mean when I say, like, sometimes the only way that you could kind of give the answer to the correct number of significant figures is to write in scientific notation? Because of that, whenever you have a number in scientific notation, this part here is always going to be significant figures. You can kind of control how many you need. So in my example there on the right, if I didn't need 3 significant figures, but I just needed 2, I could simply just drop the last 0. And now I have a number that has 2 significant figures. If I just needed 1 significant figure, I could drop the 2 and the 0 and just write something like this. And now I got 1 significant figure. So as we'll see as we go through some examples and in this chapter as well, again, sometimes the only way to achieve the proper number of significant figures is to write it in scientific notation. So doing so is sometimes of advantage because you can kind of control how many significant figures. So let's take a look at some of these examples here and see what we got going on. And why don't you take a moment and write each of these in proper scientific notation. So again, take a moment and do that. Again, if you want to pause the video, you can, and we'll pick it back up doing these examples here. Okay, so hopefully you went through these and did it properly. So our decimal point is here. And again, we do need to go to the left 1 and 2 places. So that would give us 5.68762 times 10 to the 1 and 2 as our answer. Once again, as we were just talking about significant figures, this number, all the numbers here are significant, and that is why we actually kept all the numbers here. And again, we'll talk about significant figures coming up, but that is the reason why we actually kept all those numbers. Here on the next one, our decimals here, we got to go 1 place, 2 places, 3 places, 4 places, 5 places, and looks like 6 places. That's going to give us a number of 7.72 times 10 to the minus 6. Again, negative 6 here because it's a small number. Again, it's got all those zeros up front. By the way, as we'll learn as well, they are not significant either, which is why they're not included anywhere in there. And that gives us 7.72 times 10 to the minus 6. Once again, here, 12,500, no decimal written. We do assume for the purposes of significant figures or scientific notation, that it's at the end. So that would be 1, 2, 3, and 4 places over there. And that would get us 1.25 times 10 to the 4. It is a large number. We got zeros on the back end there. So that is what we do. And again, as we'll learn, those zeros at the back end here are not significant either, which is why we dropped them. Lastly here, just 1 place to the right will do it. And that'll give us 1.35 times 10 to the minus 1. Negative 1, as this is a small number in this case. So it's also really important, and it'll become maybe more apparent as well when we continue on talking about significant figures, that you don't ever want to lose any significant figures as you go from, say, scientific notation to positional notation, which is kind of like regular numbers, or regular numbers back to scientific notation. You don't ever want to lose significant figures when you're kind of exchanging those things. So that's also something to really keep in mind as you go through it. Take a look here at a couple more. We want to put these measurements in scientific notation. So once again here, no decimal, but that's where we assume it's at. So 1, 2, 3, 4, and 5 places. Going to give us 4.25 times 10 to the 5th. We do want that unit since we do have it here, which is meters. Coming here, 1 place, 2 places, 3 places, 4 places, 5 places, 6 places, 7 places. That's going to give us 8 times 10 to the negative 7 grams. And once again here, negative because it's a small number. So we got all those zeros up front, which makes it a small number. Which is how to actually punch it into your calculator. So let's talk a little bit about your calculator and scientific notation. And I would say in most cases that I've come across, most students really don't have a clue in a sense of how to properly punch these things into their calculator. A lot of times they think they're doing it correctly, but they're actually not. And they get sometimes frustrated because what will happen sometimes, as you may experience, and a lot of students do, so don't feel bad about it. But a lot of times what will happen is you will end up punching the numbers in and you think you're doing it correctly, and you'll get the answer, and then you maybe see the correct answer and go, wow, that's pretty close. It's just off a little bit. And because it's off a little bit, it usually means that you're not really punching it in correctly. So let's take a moment here and talk about how to properly punch it into your friend, the calculator here. So make sure that you have it. Where you want to look on your calculator, and every calculator that is a scientific calculator should actually have a dedicated exponent button. And a mod calculators will look like the EE button. It will look like the EXP button. And then on some of the newer calculators, I guess they're not really new these days anymore, but years ago, they never really made them like this. But they'll have a times 10 to the N button. And usually on those calculators, it'll also have like a little wheel, upper rightish part. It kind of looks like this. I would say in a lot of cases, this calculator oftentimes comes, it gets two-tone color. A lot of times it's like white on the outside edges and like maybe blue or green in the middle. It's very commonly, these are the type of calculators that has that button. If you have these two buttons, and you won't have both of them at once, you'll either have the E button or the EXP button. Usually, I would say on most calculators, the E button is usually leftish area of the calculator. A lot of times the EXP button is kind of like bottomish a lot of times on calculators. And that's where you can find those two locations. Either you'll have, again, one or the other. You won't have both. So you'll either have one of these three buttons typically on a calculator. So let's talk first off, though, how we use these buttons here. So let's say we wanted to go 4.25 times 10 to the minus 4, and we wanted to put that into our calculator correctly. We would start just like normal. We would hit the 4, the point, the 2, the 5. Now you actually want to just hit your exponent button. So again, if you have the EE button or the EXP button, this is what you're going to push. And when you actually do that, it's really important to remember this part of it, which is when you do this button here, we'll make it nice and red. It does represent the times 10 part of the number. So basically, when you hit that button, that is what it represents. And when it represents that, that means that you do not need to do what a lot of people, and this is really where people make the mistake. And the mistake is that they will then hit the multiplication button. You do not need to do that. You should not do that. They will also sometimes, again, do like an inverse log or a second logging. Don't do those type of things either. Because that represents the times 10 part, really the only thing we have left to put in here for our number is the negative and the 4. And that brings us to another important button on your calculator, which is your negative button, which is not your subtract button. It's the plus negative button like that, or it will look like this. By the way, when you go up to this point, usually on your calculator, it'll go 4.25 and an E. It will also go maybe 4.25 and pop up a couple of zeros. Maybe even a small times 10 will be put into there. At this point, we would then do our negative button. That's going to put a negative there. And then we would go with 4, which would do a 4. And then this guy would convert over to a 4. So that is how you would properly put that into a calculator if you're using your exponent button correctly. Now let's talk about how we would put it in if we are going to have this type of calculator. Not tremendously different, except that you do need to actually start with a parenthesis. So you got to open up a parenthesis. Then you're going to go 4.25. You're then going to hit your exponent button, which for you guys will look like that. On your display, it is going to look a little bit different. It's going to put the parentheses, the 4.25. When you hit that exponent button, you're going to have a times 10 get popped in there. And then you will have like a blinking cursor up on top. At that point, you could continue the rest of it, which is the negative and 4. And you will then look like 4.25 times 10 to the negative 4. You will still have your cursor blinking at you right up there. Now, the problem is it's actually up on top and not a normal size cursor at this point. And that is where our wheel comes into place. You actually need to hit the right part of the wheel. So you take your little wheel that you have, you're going to hit that. What that will actually do is bring your cursor back down to a normal size, and you'll end up with 4.25 times 10 to the minus 4. And now your cursor is blinking right there. Now you can close the parentheses, and you'll have 4.25 times 10 to the minus 4 with parentheses that look like that. So I did go step by step, but obviously you will just kind of do that part right there, and it will get you to the correct scientific notation. Why do you need to use the wheel and bring it down? I've seen a lot of people's calculators where if you don't do that, you will end up with a number that looks like this with a small little parentheses. And a lot of times you'll get an error on those type of calculators. So you do have to kind of use the wheel to bring the cursor back down to do that. So if you do have this combination as your exponent button, there's really nothing wrong with it. It's perfectly fine. You just got to make sure that you do properly put these into your calculator correctly. And every single number that needs to go into scientific notation needs to be put in parentheses to do so. So hopefully that clears up how to do it. Let's take a look at a couple of examples here just to make sure. Why don't you take 3.2 times 10 to the minus 6? We'll divide it by 4.8 times 10 to the 12. And while we also do like 4.3 times 10 to the minus 4 times 3.2 times 10 to the 7. And see what you come up with. So take a moment, punch them in correctly into your calculator using your exponent button and see what you come up with. Okay, so hopefully you took the opportunity here to punch these in. So let us talk about, first off, that. So again, we want to make sure we use our exponent buttons here when we're punching these in. So if I were to punch it in 3.2, once again, going to hit the exponent button, and this is a -6 here. So we're going to use our negative button and then 6. And again, that would basically take care of how you would punch that in. No extra multiplication buttons or anything like that. I'm going to hit the divide button because that is what we're doing. And I'm going to put this number in the same way. That's going to be 4.8. Once again, exponent button here. This is a positive exponent. So I'm just going to roll a 12 in there. No need for the negative and hit equals. And grab my calculator, see what we got going on. Since I just made this up, 3.2 exponent button, negative button, and 6 divided by 4.8 exponent button and 12 hit equals. On our calculator here, you get something like 6.66666, lots of sixes and a 7 at some point. There's probably a few more sixes in there. Times 10 to the minus 19. This would round to something like 6.7 in this case, times 10 to the minus 19. We will talk about why that is in a second. That is 6.7 times 10 to the minus 19. By the way, actually on my calculator screen, 6.666, a whole bunch of sixes and sevens. I actually have an E minus 19. And that's really what I see on my screen. Remember that E does represent the times 10 part. So when we do write it in scientific notation, we do not want to use the E. We do want to write it as times 10. So do not write 6.7. So you should not write something like this when you're given an answer. You need to turn that E back into the times 10 part. Also really important not to miss that part of the number. It is very common. Sometimes people will just take the front part of the number and forget all about the times 10 part. That sometimes happens a lot with calculators, especially if you look at your display. You'll have a lot of the numbers in there. And then like way over here, it'll just say like, and sometimes there will just be a space like minus 19. And sometimes people forget all about that second part and need to make sure you put that together. Make sure you don't forget that when you're looking in the screen. Taking our next one here, and we're going to put it in to our calculator. We'll start here and we'll go 4.3. Once again, we're going to use our exponent button here. That's going to take care of the times 10 part. We have a -4, so we're going to use our negative button and 4. We're going to hit the multiplication button here because that's what we're doing in terms of the math part of it. That is actually for this, not any part of the number. We're going to put this guy in the same way. We're going to go 3.2. Going to do a little exponent button action there. This again is a +7, so just 7, and hit equals. So that is the way that you want to do that. 4.3 exponent -4 times 3.2 exponent 7. Going to give us a number of, on my calculator, 13760 here. And we'll do a little sig fig action here. Probably should end up with something like 14,000. Or if you want to do a little scientific notation, 1.4 times 10 to the 1, 2, 3, 4 would be the proper way. And again, later on, we'll talk about how we end up there in terms of significant figures. Just to, for those people that have the other type of calculator, we'll do this last one the way that you need to kind of punch it in. If you have the other calculator, you would have to open a parentheses. You would do the 4.3. You would hit your times 10 to the n button. You then would hit your negative button. You would then hit 4. You would then take your little wheel at that point, hit the right-hand button, and then you would close the parentheses. You then would hit the multiplication button. Once again, you would open up a parentheses for our second number here, and you would do a 3.2, again, hitting your times 10 button. This case, again, is positive, so no negative needed. Just going to hit 7. Once again, you're going to hit your wheel button. And again, you're going to close your parentheses and hit equals. So again, if you have that other calculator, the kind of two-tone calculator, all you have to do again is do a little extra work there in terms of how you would punch it in. So hopefully you got these answers. Once again, if you do find yourself very close to the numbers I got, and what will usually happen is, for example, this part of the number looks good, but this part is like off by like 1 or so. That's usually the way that you're punching it into your calculator. You're adding some extra step there somewhere along the way that you shouldn't be doing. Usually that's like hitting the multiplication button or something else weird like that. So 100% of the time in all chemistry classes, this is all levels of chemistry classes, by the way, there's people struggle a lot with how to punch it in scientific notation into their calculator. So make sure that you practice this. Make sure that you understand how to do that. Obviously, you could reach out to me if you're not sure, or if you're not sure where your exponent button is on your calculator. We could probably figure it out, and make sure that you do know how to properly punch these in. Half the battle of a lot of chemistry is the calculator, and how to properly use it, how to properly punch things into the calculator. That's a lot of times half the battle for a lot of people. So you want to make sure that you are, again, following along as we do these examples. These are one of the reasons why it's really important to do that with the calculator that you're going to use on an exam or quiz, because then you'll know if you're actually punching these things in correctly. So again, another very important reason why you should be actually working these things out yourself and making sure that you do get the right answers. All right, so let's talk a little bit about measurements and the uncertainty in measurements. So when we do have measurements, regardless of the measurement that we take, there's always going to be some degree of uncertainty when you take a measurement. So the degree of uncertainty really will depend on the piece of equipment that you're using. And that will also determine how far you can take an actual reading. So for example, if you were to look at something like a ruler, and we got one there, and we'll go. We'll put a 2 there. We'll make these like centimeters. Create this ruler, maybe. And let's say we have this ruler, and let's just say that we wanted to sort of measure. We'll go with this guy right about there. Not ballpark. Now, when we look at a measuring device, say a ruler, graduated cylinder, any piece of equipment that you're going to use, that has markings on it. There's usually two types of markings that you see. So usually when you look at a piece of equipment, there's usually two types of markings. There's sort of the large marking and what is sometimes referred to as the small marking. On this particular ruler that I drew, the large markings are the ones that actually have numbers. So that's a 1 and that's a 2. And the difference between the two large markings is 1 centimeter. So kind of the large markings on this ruler that I drew is 1 centimeter. Now, there's also usually smaller markings that you can find on a piece of equipment, and you do want to count those as well. Now, when you go to count the smaller markings, it's really important to actually start counting past the last large marking. So what I mean by that, in this case, the last large marking on my ruler I drew is 1. So I'm going to start counting at the marking next to it, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you want to stop counting once you get to the next large marking. So I actually have 10 small markings between the 1 centimeter large marking. And if I divide basically 1 centimeter by 10, that tells me that each of the smaller markings represents, in this case, 0.1 of a centimeter. That means that this first marking would be 1.1, this guy would be 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2 as we go all the way across. So once we figure out what the large markings represent, and once we figure out what the small markings represent, we're ready to really start to take our reading. Now, whenever you use any piece of equipment, regardless of who takes a look at it, there's always certain markings that everybody would agree upon. There's like kind of no argument. No matter who looks at it, everybody should definitely agree it is at least this much. And if we look at my example here, we could clearly see my line is at least 1.3. And we definitely would record that as 1.3. These numbers here are what are sometimes referred to as all of the certain numbers. And the certain numbers in a measurement, once again, are pretty much no matter who looks at it, there shouldn't be any type of argument. Everybody should agree it is at least that much. But now when I look at my actual line that I drew that I'm trying to measure, I could see it's not exactly 1.3 and it's not exactly 1.4. It's somewhere in between those two. This is where the uncertainty comes out in the measurement and really the estimation. Now, somebody, say like me, will look at it and go, well, it kind of looks like it's in between both of those numbers. And I would record like a 5. Somebody else may look at it and go, nah, I don't think it's exactly half. Maybe it's a little less than half. Maybe it's a 4. Maybe it's a little bit more than half. Maybe it's a 7 or it's closer to the 1.4. Maybe it's an 8 or something like that. So that is where the uncertainty lies. And this is what is sometimes referred to as the first uncertain number. And obviously here we would record our units of centimeters. So here we would record 1.35, which is all of the certain numbers. And that first uncertain number, and that is 1.35. The reason you want to do that and the importance of doing that is when you record all of the certain numbers plus that first uncertain number, that frankly is what significant figures are. Which means this measurement that I just made has 3 significant figures. All those numbers are significant. It's assumed that it's kind of like plus or minus one of the last significant figure that is there is sort of where the arrow is. So when we record something like 1.35 centimeters, for the most part, we're really saying, I think it's like 1.35. Maybe it's like 1.36. Maybe it's 1.34. That is where the error really in the measurement is. Now, when you are taking measurements, it's also really important to always look at your scale. Not all scales will be the same. So, for example, let's say we were going to take a volume measurement here, and we'll draw a really bad graduated cylinder. That is so bad, I'm going to erase it. That's how bad that is. And I'm going to give it the old college try one more time, maybe. All right, that's a little bit better. Not much. That's how I failed art 9 times, but that's all right. That's another story for another day. Let's say we have a 10 there. Do a 20 there, and we'll do milliliters as our units. And why not? Let's put a little bit of water or something in there. Let's go with a bit of water level about there. By the way, when we do put a liquid in a glass container, we will typically see the curvature of that liquid. And we'll talk why that is in a later chapter, but that is sometimes referred to as the meniscus. And when we take a reading on the meniscus, we always typically, especially when it's kind of this U-shaped, we always read from the bottom of the meniscus. It's always where you want to read. Not all meniscuses will always be to U. Most of the time it will be U. Some meniscus actually go the opposite way, but most of the time it's going to have this U-type shape. For example, mercury actually goes the other way. If you had something like mercury, you actually would read from the top of the meniscus there, as I missed it very badly there. But in most cases, you're going to see this U, like water and other substances, and you want to always read from the bottom of the meniscus because that's really where the volume level is. And in a later chapter, we'll talk about it. So once again here, if we take the look at the scaling here, we got 10 as a big number, and we got 20. So our large markings in this case is actually going to be 10 milliliters. Once again, we're going to count the small markings between the larger markings, and we're going to start again just past that last large marking. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So we have 10 markings, once again, between the large markings. So again, if we take something that writes, we have 10 milliliters and we have 10 small markings divided by 10. That means each of the small markings represents 1 milliliter in this case. That means this guy here is 11, 12, 13, 14, 15, 16, 17, 18, 19 as I squeeze it in there. And then obviously up to 20. So in this case, we're going to take a look at where we are in terms of our meniscus. Maybe we'll go with this. So if I just kind of draw a line, again, straightish as I can do, we could see that it is at least in this case 11, 12, 13, 14, 15. So we would record 15 here. These again are our certain numbers. Once again, it's not exactly 15. It's not exactly 16. So this is where the estimate comes into place. So maybe in this case, I don't feel it's exactly half. Maybe I feel it's just above the 15 mark. And maybe I feel it's like a 3. And I would again record my milliliters as my units. This would be my first uncertain number. That means in this case, this number has 3 significant figures here. All of them are significant. Now, it's important to remember that even if you're even using the same piece of equipment, so even if you're still using the same, say, graduated cylinder or a graduated cylinder, two different graduated cylinders, the scaling on it may not always be the same. So, for example, if I draw once again a fairly challenged looking here graduated cylinder, this is not looking so great. We got a 10 milliliters there. We'll go with bad quality control apparently at this factory. So we have, in this case, on this graduated cylinder, let's put some liquid in it. Maybe hide the bad artwork here. We'll go here. We'll go right about there, maybe. All right, so now in this case, we still have our large markings is going to be 10 milliliters. Now when we count up our smaller markings, that is 1, 2, 3, 4, and 5 only in this case. So in this case, we actually have only 5 markings. So we have 10 milliliters divided by 5. That is going to tell us that each of the smaller markings in this particular case is actually 2 milliliters. That means that this first line here is actually 12. That's 14. That's 16. That's 18. Like I'm doing a cheer. 2, 4, 6, 8, 2. We appreciate. And that means that when we look at our liquid here, coming through a straight sort of ish line. Now we're actually sitting right about here. And when we look at this particular case, we now have 14 and then it jumps to 16, which means between 14 and 16, that value is 15 is the number that is between 14 and 16. So why can't we go, it's like 15.2? The reason we can't do that is there's really no way, if we just super zoomed in between 14 and 16, there is not enough room between those two markings to go. I'm not really sure where 14 ends, where 15 starts, where 15 ends. There's not enough room to visually do that, as opposed to the previous one where we had maybe 15 and then 16. Here we can imagine it's only basically a difference of 1. So we could figure out, okay, it's definitely 15 point something above that 15 line, and it's definitely less than 16. So you could kind of evenly break apart that distance and figure out whatever it is. But here, since we have kind of a 2-number jump, we're not really sure where 15 begins, where it ends, and where all that kind of stuff. 14 ends and begins. There's no way to kind of visually break it up enough that you can make an extra reading. So in this particular case, the best you could do is actually 15 milliliters. That means that if we were to look at this measurement, it would actually have 2 significant figures, where the 1 is our certain number. And actually the 5 here is our uncertain number, or as the estimated digit. So it does depend on the piece of glass we're using, the scale that's on there, as to how good or bad of a measurement that you could actually take. And you do want to, speaking of taking, you do want to take the time to figure out, how far you can take that reading. The general rule is you could typically take the reading to one more place to the right of the smallest marking. So typically speaking, that is what you could do. One more place to the right of the smallest marking. So we see that here, for example, in our first example, smallest marking is to the first decimal place. We could take the reading one more place to the right, which is exactly what we did. We went to the second decimal place. We see that here on the second example. Smallest marking is 1, which means we could go one more place to the right, which would be 0.1. And that's exactly what we did. But here you cannot do that. So you do have to sort of figure out how far you can take the reading. 9 times out of 10, one more place to the right of the smallest marking is where you probably should end up in terms of your reading. So let's take a look though at another example here. And let's say we had our ruler like we had before. And we'll connect my straight-ish ruler here. There we go. And we're going to take a measurement of this line. Let's just go. We're going to be dead on that marking right there. All right. So why don't you do this? Why don't you take a reading and decide what is the proper reading based on the scale as to what you should end up with. So take a moment here and try it yourself. Okay, let's take a look at this. So once again, we still want to do our normal sort of process here. So just like we did previously, we're going to come up the same way. Our large marking on this guy is going to be 1 centimeter. Once again, counting our smaller markings, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, gonna give us our small markings of 0.1 centimeters. Again, divide that by 10, get you there. So just like we saw previously here, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, and a 1.9 as our markings. So now when we go to record this, definitely is on that 1.4 in terms of what we see. So what should we record? 1.4 centimeters, 1.40 centimeters, 1.40000000. It's not caught in a loop. I'm just saying a lot of zeros. Centimeters in this case. I'm going to say maybe that's a little too many zeros just to say that. Sometimes extra zeros is not always the best thing. So which one is it? Is it number 1 here? Is it number 2? Take a moment. Hopefully you have the right one on your paper. And the survey says it is this guy. And why is it this guy? And is there a difference between writing the guy here on the left or the guy on the right? So let's talk about why it really is the guy on the right here, and is there a difference between them? And the answer again is there actually is. So if we were to say, I think it is the first one here, I think it is this guy right here. That means that this would have 2 significant figures, with the uncertain number being the 4. So what that is really saying is, I think it is 1.4 centimeters. Remember, the uncertainty there is in that last sort of significant figure, but you could be saying, well, maybe it's like 1.5 or maybe it is 1.3. And clearly that is 1.3 there. That is 1.5 there. And frankly, neither of those markings is near where the actual line is. They're far away. That is a lot of uncertainty there. Now, if you take this guy, this is all of our certain numbers. That means that that has to be my first uncertain number. And this guy would actually have 3 significant figures, with the 0 here at the end being the uncertain number. What you're saying is, in this case, I think it's 1.40 centimeters, but maybe it's like 1.41 centimeters. Maybe it's 1.39 centimeters. The error here is pretty much what we actually see on the ruler. And that is why it is important here to keep the 0 at the end. And that is because on this particular scale, we have the ability to do that. We have the ability to go one more place to the right. So even if we find ourselves, which oftentimes happens when people take measurements, like I think it's like right on the line. So they go, it's not a big deal. It's 1.4, 1.40. It's 1.4. It doesn't really matter. It does matter. You actually made your measurement when you lop off that 0 and you record it like this. For a lack of a better description, you just made that a pretty crappy measurement. Yeah, there's a lot more error. You're basically saying, well, I'm not really sure where this line is. It's somewhere between like this area. That's a pretty big area of, it's somewhere in the ballpark there. It's not very near where it's at. When you keep that 0, which you should do in this case, because you have the ability to do so, you are making your measurement much, much better. You're saying, no, it's like in this area. That is pretty much our degree of error here, right? So sometimes people think it doesn't really matter when you're taking measurements that, if it's dead on the line, that you don't maintain the proper number of significant figures. But every time you remove a significant figure from your measurement that you should not do, again, you're making that measurement a lot worse than it should be. It's a much worse measurement with a lot more error associated with it than it should have. So that is something to definitely keep in mind. You never want to get rid of zeros if you're able to do that. So when you take measurements, there's some degree of uncertainty. You got to make sure that you always record it to the proper number of significant figures, and you always want to look at the scaling. Now, just a note that if you are using something that is digital and has a digital display and just gives you the value like a balance, which is a scale, and it just tells you what the numbers are, that's also a place where people screw up in terms of recording measurements. You should always record all the numbers on a digital sort of display. They are usually there because they're important. So don't do that. If you go to a balance to weigh something and it's like 52.365 grams, you just record 52. Again, those other numbers are really important as well. So one last thing here about looking at scales and figuring out how far you could go. Again, the general rule is you really can just go one more place to the right of the smallest marking. If you're not sure still like how far you should take the reading, the one thing that you can do is if you are able to figure out what the smallest marking represents, all you have to do is take the smallest marking and divide it by 2. And if you take the smallest marking, for example, here, 0.1 and divide it by 2, you will end up with 0.05 centimeters. That's basically 2 decimal places, and that's essentially how far you should take that reading. Sometimes people may even record the value as 1.40 centimeters plus or minus 0.05 centimeters, and that kind of tells you how far you can take that. That little trick works for everything that we did before. Once again, if we come here to the one we did previously, smallest marking is 1 milliliter. Divided by 2 gives you 0.5 milliliters, which is 1 decimal place. And that's exactly how far we took the reading to. So once again, sometimes people will record 15.3 milliliters plus or minus 0.5 milliliters. For our purposes here, you don't have to record the plus or minus, but you could use it to figure out how far you need to take the reading. Even on tricky things, like our smallest marking on this one was 2 milliliters. If I take the 2 milliliters and divide it by 2, that tells me 1 milliliter, which is the whole number, and that is exactly what I took the reading to. So if you're not sure how far you should take the reading, like I mentioned, general rule of thumb, most of the time, one more place to the right of the smallest marking. If you're still not convinced or not sure, but you can figure out what the smallest markings represent in terms of value, all you have to do is divide it by 2, and you should take your reading to however far out that goes. So again, either 1 decimal place, whole number, 2 decimal places, whatever it may be. All right, so hopefully that clears up how to properly take measurements. And this is really where our significant figures sort of come from. And again, here's some examples of measuring our ruler. our nail here. And again, we sort of envision breaking that little part up to give us a last digit that we need. So as I mentioned, it is custom to record all the certain numbers and that first uncertain number. And again, when you do so, that is essentially what significant figures are. It is plus or minus 1 are the estimated digit, by the way. The estimated digit is not always, by the way, the last number that you write, but it is the last significant figure that you write. So that's two different things. It may not make sense right now. We'll maybe see an example of that. But when you think about the estimated digit, again, it is always the last significant figure, not always the last number that's actually written in a measurement. So let's talk a little bit about taking measurements and the difference between accuracy and precision. And there is a difference between those two. So accuracy tells us how close a measurement is to the true value, and precision tells us how close a set of values are to one another. So accuracy tells us how close we did to what we should get, what the actual value is. Precision a lot of times tells us how much a group of numbers are to each other. And a lot of times we use precision to think about how reproducible something is. For example, when you do experiments, a lot of times you do multiple experiments or multiple trials, I guess is a better way of saying that. You do the same experiment multiple times, and we can look and see how reproducible, how repeatable that experiment can be. So a common example to illustrate this is the bullseye. So if we had a bullseye board here playing a little bit of darts, and when we play darts, the goal here is to get the bullseye in the middle. And if I take my 3 darts and I throw my darts and I throw one here, oh, I missed the dartboard. I'm a pretty bad dart thrower there. Am I accurate? The answer you should say is no, I am not accurate, right? The goal is to get the bullseye in the middle. Am I precise? Not so much either. I'm pretty much all over the place. So none of this is repeatable. And I missed the board. Hopefully nobody's standing there. So I go, all right, no big deal. We'll just kind of do a double or nothing here in a friendly sort of situation here. And I take my darts and I throw them and I go boom, boom, and boom. And in this particular case, am I accurate? Hopefully you are shaking your head. No, I am not accurate because, again, I am nowhere near that bullseye, which is the true value. Am I precise? You hopefully should be shaking your head. Yes, I am precise. I am precisely not accurate. Yes. So this demonstrates a very good idea that you can definitely be precise and not accurate. What's the old saying? You could do the same thing wrong every single time because you think you're doing it right. So you could continuously be very consistent in the mistakes that you are making, and you could end up with the same answer over and over again, but it may not be the right answer because you keep making the same mistake. So I go, all right, we'll go, we're up to triple or nothing, I guess, right? I think is where we're at. So I take my darts and I throw them and I go boom, boom, and boom. And am I accurate? At this point, you should be nodding. Yes, I am accurate. I hit the bullseye all 3 times. Am I precise? I am very precise. I also put all 3 of them pretty much in the same location. Was very reproducible. Did I hustle you there? Maybe I did. Never go triple or nothing. I suppose nothing good come of it. But in this case, that is essentially what we're looking to do in chemistry for sure, and in most sciences when you do experiments. You do want to be very accurate, so you do want to kind of get the right answer. You do also want to be very precise. That allows you to repeat your experiments over and over again and have that reproducibility. So you want to usually be both accurate and precise. You don't necessarily want to be very precise and not so accurate as we saw in the previous one. And sometimes in chemistry, we do look at certain things to figure out, accuracy and precision. And we'll probably talk about maybe along the way, but something like percent error is something that we look at in terms of how accurate we are. And we use that to compare how close we are to the true value. Percent standard deviation or percent precision is something that we look at when we look at how reproducible something is. So we've been talking about significant figures here with measurements. So the formula here, talk about significant figures and how to count significant figures. Let's take a look at these rules. So the rules for counting significant figures pretty much is as follows. Any non-zero number will be significant. When we count numbers, and especially when we're counting for significant figures, we always start left to right. And as soon as we hit the first non-zero, that is when you should start counting your significant figures. So right here is our first non-zero going left to right, and all four of those are non-zeros, which means this guy has 4 significant figures. All 4 of them would be significant here. Now, zeros, there's several different types of zeros that we come across. The first type is a leading zero, and those are not significant. So when we look at this number here of 0, we're not going to count yet. We're not counting. Boom, we hit the 4. That is our first non-zero number. That is when we should start counting. So the 4 and the 9 here are significant, which means this has 2 significant figures. The other ones are just sort of placeholders. We don't count them because we have not hit the first non-zero yet. There are captive zeros, or sometimes referred to as trapped zeros, and these are zeros that are between 2 non-zero numbers. They are also going to be significant. So here, starting to count at the first non-zero, which is 5, here we have our trapped zeros, which are significant, and our last number, which is significant, gives us 4 significant figures in this case, and they would all be significant here. Now, the last type of zero is really the one that gives people really the hardest time, and that is a trailing zero, and they may or may not be significant, and they are only significant if there is a decimal place written, or decimal point written in the number. The decimal point does not need to be near the zeros that come at the end, just needs to be written in the number. So 600 written like this. This is our first significant figure. These are trailing zeros here, and these guys are not significant because there is no decimal point written. We do not assume, in the case of assigning significant figures, that there is a decimal point at the end, like we do when we're kind of moving to do scientific notation. If it is not written, it is not there, and we don't count it in that case. So here, this would have only 1 significant figure written like that. Now, if we write it like our other one here, this is significant. Now, these guys at the end are going to be significant because there is a decimal point there, and this guy would have 3 significant figures in this case. So that's really important when you go to count them. So, for example, if I had something like this, 0.0004003, 0.000300000. Why don't you figure out how many significant figures there would be in this measurement? Let's call it meters, if you somehow were able to measure that way. So take a moment, figure out how many significant figures there are. I'll take a moment as well because I just wrote it. I have no idea. Let me count with you probably. All right, so here we're going to look not interested because we have not hit non-zero yet. Still haven't hit non-zero. Boom, F this 4. That is where we're going to start counting. So that is 1 significant figure. These are 2 zeros that are trapped, which means they are significant. This 3 is significant. These 3 zeros are trapped. They're significant. This 3 is significant as well. So up until this point, we have 1, 2, 3, 4, 5, 6, 7, and 8. That now leaves our zeros here at the end. Are they significant? Again, hopefully you are shaking your head. Yes, they are significant because way over here, there is a decimal point written. Once again, does not need to be near those zeros for it to be significant in this extreme example. But this would be significant, which means I lost track there. We'll start again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and lucky number 12. There is significant. So that takes care of all the zeros. Now you may be saying, what about these zeros here? Let me highlight them maybe. What about like these zeros here? Aren't they after the decimal? Shouldn't they be significant? The answer to that, if that is your question, or you do have that question, is we have not started counting at that point. So remember that we did not start counting until we got to the 4, and those came before the 4. So those, even though they are after the decimal point, those are still considered leading zeros and not being significant because we have not started counting until we hit the 4. So a lot of times people have that question. Now, let's say I had something like this, 12,000. Here's the question. How many significant figures are there? We'll do 12 as well. And which one is the estimated digit or the uncertain digit? So take a moment for each of those numbers that I wrote there, 12.0 and 12,000. How many significant figures does each of those have, and which ones are the estimated digit in each of them? So take a moment and decide that. Okay, let's start with the first number I wrote. The way this is written, we would start counting here. We would go here. These are going to be trailing zeros. There is no decimal there, which means this number here, the way it is written, if it was a measurement, has 2 significant figures. The estimated digit in this number is actually the 2 here is the estimated digit. Again, it is not the last digit that is written. It is the last significant figure that is written, and that is 2. The other ones are kind of like placeholders to keep the value the same, but the 2 there is actually the estimated digit. Now, when we look at this guy, this is significant, this is significant, this 0 here is going to be significant as well because of the decimal point. So this would be 3 significant figures. And the uncertain number here, or estimated number, would be the last 0, would be our estimated digit. So as I was mentioning earlier, not always will it be the last digit that you write. I would say like 90% of the time, maybe even higher, it will actually be. But it is definitely always going to be the last significant figure that's in that number. And that's why in that case of the 12,000, it's actually the 2 where the uncertainty is. That's also why the 12,000 is maybe a worse measurement, because we're basically saying, I think it's 12,000, but maybe it's like 13,000, maybe it's 11,000. That's a pretty big area of error between that measurement, as opposed to the 12.0 where we're saying, I think it's 12.0, but maybe it's 12.1 or 11.9. That's a much smaller area of error. So hopefully that clears up a little bit about estimated digit and where you find it. Now, the last type of number are exact numbers, and exact numbers are basically achieved one of 2 ways. They're either achieved by counting or they're definitions. So, for example, if I had like 3 pens on my desk, I'm not going to do some type of scientific experiment to figure out how many pens I have on my desk. I'm just going to simply count 1, 2, and 3 and go, cool, I got 3 pens. I'm all good to go. Now, the other way, more commonly, how we come across exact numbers is in definitions, like 1 inch is exactly 2.54 centimeters. So that is what is referred to as an equality. An equality are two things that represent the same amount of something, but are on different units. And that's also a definition, and that is also considered an exact number. So what is the deal with exact numbers? Exact numbers can have an unlimited number of significant figures, which means they could have as many as you want because they're exact. So what that means is typically in calculations, as we'll talk about, we do look at the significant figures of everybody that's involved in the calculation. If you come across something in a calculation that's considered an exact number, you actually ignore it in terms of looking at how many significant figures your answer should have. So when we get to calculations involving significant figures, we actually ignore anything that's an exact number, as it's not going to be important in terms of our answers. So, and that's because it could have multiple amounts of significant figures. So let's take a look at a couple of these examples here. So take a moment and figure out how many significant figures each of these guys have. Okay, so hopefully you did. Let's take a look. Once again, starting left to right, we're going to roll this way. Boom, at the 3, that is where I'm going to start counting. That's my first non-zero. I got me a 0 that is trapped, and the 4 is a non-zero, so that's going to give me 3 significant figures here. This is a number that is written in scientific notation. That is all the numbers that come before the times 10 part like we talked about, and that is going to be 4 significant figures. By the way, if you were to do this as 1.270 times 10 to the 2, and sometimes people go, oh, let me just convert it into a number. So 127. Oh, it has 3 significant figures. Wrong. So we want to count the number of significant figures when it is in scientific notation, not when you convert it back to a decimal. Remember, as you go back and forth between those, you shouldn't lose any significant figures, which means if it has basically 4 significant figures in scientific notation, it should also have 4 significant figures in decimal place, which means if you were going to convert this, 127.0 has 4 significant figures, and that is what you would maintain. Speaking of scientific notation and writing numbers, as we talked about before, let's say we had 12,000 and we wanted to write 3 significant figures, right? And give the answer in 3 significant figures. There's no way to do that. You can't go 120, right? Because 120 with a decimal is 3 significant figures, but there is a big difference in those meanings. So you can't do that. So really the only way, for example, if you wanted to get this into 3 significant figures, 1, 2, 3, 4, is you would have to write something like this here to get it into 3 significant figures. So as I mentioned earlier, sometimes the only way to get it to the proper number of significant figures is to write a scientific notation. There would be no way to write 12,000 with 3 significant figures and still have the right meaning. So you want to make sure you keep that in mind. Here, that's significant. All those are significant. That's 3 significant figures. That is a 1, which is significant. There is no decimal written here, which means the 0 at the end is non-significant. So that is 1 significant figure. And lastly, here, we're going to not start until we hit our 9. That's trapped, which is significant. The 2 is significant. The 0 is significant because way over here, there is a decimal point there, which means the 9, the 0, the 2, the 0 are significant. Gives us 4 significant figures. A reminder in terms of calculators as well, we do not always get the answer to the right number of significant figures in our calculators. We may have to convert the numbers to the proper number of significant figures. Taking a look here to finish up here, talking about some significant figures, 155, those are all going to be significant. That is 3 significant figures. A basket of 8 apples, that's going to be something that you count, which means it's going to be an exact number. By the way, if you weighed a patient, that would be a measured number. I guess I should read the question. That probably would help as well. 1 kilogram is equal to 1,000 grams. That's an equality. and that would fall under an exact number, unlimited number of significant figures. And the distance between Denver and Houston, 1,720 kilometers, that would be a measured value in this particular case. All right, so let's talk a little about rounding, which is really important. So normal rules of rounding happen. If it is less than 5, basically, we just kind of drop the numbers. And if it's more than 5, we do round up. You do want to avoid crazy rounding. So for example, here, if I have 13,333, and I want you to round this to 2 significant figures, why don't you take a moment and see what you come up with in terms of your answer? All right, so I can hear you yelling out there the answer. Maybe. Maybe somebody yelled, it's 13. Maybe somebody yelled, it's 13,000. Is there a difference here? Let's take a look at these and see. This is 13, which is 2 significant figures, as they are both significant. This is 13, which is significant. These are not significant, as I did not put a decimal point there. So that would be 2 significant figures. So I guess they both have 2 significant figures. Then I guess they're both the right answer. Wrong. Not so much. So let's see why that is. Let's just say this was money here, and I owed you $13,333. And I said, you look like a good chemistry student. I'm just going to give you 2 significant figures. Here's $13. We're good. We're even. Thank you very much. Shake your hand, walk out the door. Probably not so much there, I don't think, right? So there's a very big difference, right, in the meaning of, say, $13,333 and $13. So although it does have 2 significant figures, you have definitely changed the meaning of that number, which you never want to do. So you never want to change the meaning of a value by doing extreme rounding. And that sometimes happens because people are so focused on the significant figure part that they just like lop off numbers and just round to get to the right sig fig. So you never want to do that. But now if I owed you 2 significant figures and gave you $13,000, maybe give me the $333 teacher discount and it's probably okay, hopefully. But it's relatively the same number, 13,333 and 13,000 has basically the same meaning. So you would go with this. So when you are rounding, you want to be really careful. People, again, very often try to so hard to get the correct value that they end up kind of rounding too much, and you don't want to do that. Other place you don't want to round too much is if you're doing a bunch of calculations and you're going to get an answer, take that value and continue on in the calculation. Get another answer, can take that answer, continue on with another calculation. You really don't want to round to the very end. You want to kind of keep track of everything and then kind of clean it up to the right number of significant figures there at the end. Otherwise, every time you round a little bit, you will find yourself moving kind of farther and farther away from the correct answer. So here, if we want to do each of these to 2 significant figures, why don't you take a moment and think about it? Okay, so hopefully you did. 2 significant figures would take us here. We would look at the 7, which is above 5, and we would round up, and this would be 36 meters. Once again, our second significant figure would be to the 8. We would look at the 2, and in this case, we would get rid of the other numbers, but we cannot write 38 because, again, that's a big difference between 38 and 3,800. We do have to actually keep the zeros as space holders for 3,800 and put grams. Now, am I tempted to put a decimal point at the end? Maybe you are, but if you do that, you then don't have 2 significant figures. You would have 4, which is not what we're looking for in this particular case. Here, we're not going to count until we hit the 2. That means the 6 here is actually our second significant figure. We would then look at the 2 that's next to it and drop it, 0.0026. Here we would not put the extra zeros at the end for the same reason, because there's a decimal point at the beginning. If I put those 2 zeros at the end, I now have 4 significant figures, which again is not what I'm looking for in this case. And lastly here, the 2 being our second significant figure, looking at the 8, which is above 5. So we're going to round up. That's going to give us a 1.3, which is 2 significant figures. So again, you want to be careful with significant figures. You want to do too much crazy rounding. All right, so to complete our sort of conversation here about significant figures, let's talk a little bit about it in calculations, which is kind of an important thing. There's really kind of 2 sets of calculations that we do. When we multiply or divide, what we're looking at is the significant figures, and your answer when you multiply or divide, your answer should have the same number of significant figures as the number with the least number of significant figures. So if you were to take 1.2 times 3,222, that is 2 significant figures times 4 significant figures. My answer should end up with 2 significant figures. Now, if you add or subtract, what you're looking at is decimal places, not significant figures. And it's the least number of decimal places. So your answer should have the same number of decimal places as the number with the least number of decimal places. So let's just say I was taking 1.1 and we're going to add it to 2.22. We're going to add it to 3.333. Very creative there. And try it without the calculator. That's going to be a 3. That's going to be a 5. That's going to be a 6. And that's going to be a 3, 5, and a 6. So here we went to 1 decimal place, 2 decimal places, 3 decimal places. Our answer actually should go to 1 decimal place. It is a 5, which means 6.7 should be our answer here. 6.7 has 1 decimal place, but it has 2 significant figures in case you need to know that. And that might be important if you're going to take that number and do some type of multiplication with it. Let's take a look at each of these and kind of see where we should round off to. Here on our calculator, which once again will not give us the proper answer all the time. So we do have to kind of look at it and make sure we report it to the right number. We are multiplying, so sig figs is what we're looking at. 3 sig figs, 2 sig figs. Answer should have 2 sig figs. That's going to go there. And that's going to look at the 7, which means 9.4 is what we should have. Here we're dividing, which means, again, significant figures. This has 4 significant figures. This has 3 significant figures, which means our answer should have 3 significant figures. That is going to take us to the 8. We're going to look at the 2 and drop the rest of the numbers, which will take us to here. We are adding, which means we're looking at not significant figures, but we're looking at decimal places. So here, this has 2 decimal places, 1 decimal place, 3 decimal places. We're going to look at 1 decimal place in terms of our answer, and that's going to give us a 29.1. Has 1 decimal place, but 3 significant figures. Lastly, here we're subtracting, so that is 4 decimal places and 1 decimal place. Going to go to 1 decimal place, which will give us 0.6. Because of the 8, we're going to round up, and that will be 1 decimal place in this case. So it's also important that if you are doing multiple steps that you keep track of it. So for example, if we took 32.5 times 0.5, there we go, times 1.2 and divided it by 4,536. The first thing that we would do would be what is in the parentheses, which is multiplying. So really this would be 3 significant figures times 2 significant figures, which means really our top number should have 2 significant figures. Then we're going to take our top number, which is 2 significant figures, and divide it by our bottom number, which is 4 significant figures. And that means our answer actually should end up with 2 significant figures. So if we do that, 32.5 times 1.2 divided by 4,536 gives us this number, 0.008597884. So really we should end up right here, which means we should round 0.0086. And again, up on top there, we ended up with 39, and we're dividing it by 4,536. Got us down here. So you do want to keep track of it. Again, I would not round a lot until the very end. Sometimes people put a little line above where they should go, but you should keep it a track. Even if you're doing multiplying and then maybe adding. So if you had something like 333 times 4.2, and then you're going to add it to 1.225. So here we would do this first. This is 3 significant figures. That is 2 significant figures. So we got 333 times 4.2, going to give us 1398.6 plus 1.225. Technically speaking, this should end right about there. I personally would not round at this point. I would actually take the whole number and then add it to 1.225. And that's going to give me on my calculator 1399.825. So how do I basically figure out where it should be? Well, I know that I should have ended this number here, which is basically 1400, right? And then I'm adding it to this number here. And now I should be looking at actually decimal places. That's 3 decimal places and actually no decimal places, which means really I should take this answer to no decimal places and round it up to 1400 in this case. So that is where we should really end up in terms of our answer. And you do want to kind of keep track of it along the way. So sometimes you will kind of mix and match, multiplying and dividing, adding and subtracting. Once again, multiplying and dividing is looking at significant figures. It's the least number. Adding and subtracting, you're looking at decimal places, also the least number. And again, they're both the smallest or the least number because that is frankly your worst measurement. And your calculation is only really as good as your worst measurement. So that's why we always look at sort of the least. All right, well, I think that's a good place to kind of stop here and put a little note here on chapter 2 so far. We'll continue on with another recorded lecture. So we'll see you next time. Thanks for watching. Have a good day, night, or evening, or morning, I guess, if you're watching in the morning. And we'll see you on the next one. Bye for now.
Hello, did you hear the one about oxygen and potassium going on a date? They went on a date. How did it go? It went okay.